Hello everyone, welcome back. In this video, we're going to talk about the cross product, which is an important way to multiply two three-dimensional vectors together to produce another three-dimensional vector. So there's a lot of ways to motivate and define the ideas behind the cross product, but we're going to go ahead and do so using the concept of torque. So we can think of torque as a turning effect that is produced whenever you're trying to tighten or loosen a bolt, and that's what I'm trying to represent in this sketch that I'm drawing up over here. And so here we have our little blue bolt. This vector R is denoting like the wrench that is attached to our bolt, and this second vector F is the force vector that we're applying to the wrench, pushing the wrench that is causing us to turn the wrench around the bolt and either unscrew or tighten the bolt. And so in the ideal situation, our force vector would actually be perfectly perpendicular to our R or wrench vector here, and that would create the maximum amount of torque for a given amount of force. And so part of that idea is any part of this force vector that is parallel to our wrench vector R or displacement vector R is not going to contribute to that turning motion and creating that torque effect. So it's really just that perpendicular component of our force vector relative to our vector R that is going to create that turning effect and actually produce torque. So we'll talk about how to visualize this torque vector that is created in this situation in just a moment. But first, let's go ahead and talk about what contributes to the size or magnitude of this torque vector. So the torque vector is going to be denoted as the vector tau, and its magnitude is going to depend really on two things. So one quantity, the magnitude of the torque or the amount of turning effect that is produced in this situation depends upon is essentially the size of the wrench. Or more precisely, the distance between the axis of rotation and where the force is being applied. And so the second piece that contributes to the size of our torque vector is the amount of push being contributed by our force vector. But more precisely, it's going to be the amount of push that is perpendicular to our position vector R, right? Only that perpendicular component of our force vector with respect to R is actually going to cause any rotation around our axis of rotation or our bolt. So again, the two quantities that contribute to the magnitude of our torque vector or the amount of rotation effect that is caused in this situation is going to be the distance between the axis of rotation and where the force is applied. We're going to call that the magnitude of R or the length of our position vector R. And in our analogy, this is really just kind of like the length of your wrench and actually pushing at the end of your wrench. The second piece that contributes to the magnitude of our torque vector is going to be the amount of force contributing to the actual rotation, or more precisely, the scalar component of our force vector that is perpendicular to our position vector R that represents the wrench. So with that covered, we can now talk about the formula that gives us the magnitude of our torque vector. So our torque vector is denoted as the vector tau. And so its magnitude is going to be the product of two things. It's going to be the product of the magnitude of our position vector R, or the length of our wrench. And that's going to be multiplied with this scalar component of our force vector that is perpendicular to our position vector R. And so how do we include that factor in our formula? Well, first let's go back to our picture here and add a little bit to it. We can think about breaking our force vector up into two components. The scalar projection of our force vector onto R, and this orthogonal component of that scalar projection. And that's the piece we're actually interested in, that orthogonal component, or the component that is perpendicular to our vector R. And so in our little right triangle breakdown of our force vector F, this vertical component with how we've drawn everything here is going to be the component of our force vector that is perpendicular to R. And so let's assume that we can actually find the magnitude of our force vector. That'll represent the hypotenuse of this little right triangle that we have drawn here in blue. The height of our right triangle is going to be the magnitude of the component of our force vector that is perpendicular to our position vector R. And theta is going to represent the angle between our two vectors, our position vector R or our wrench vector R, and our force vector F that is pushing against the wrench and causing the rotation. Well, using a little bit of right triangle trig, we can see that we can relate this angle theta here to the side length opposite of it and the hypotenuse. And so sine of theta is going to be the ratio that is the magnitude of the component of our force vector F perpendicular to R divided by the actual force vector R, or at least its magnitude. And so doing a little right triangle trig and solving for the magnitude of the component of our force vector that is perpendicular to r, what we can find is that that component is going to be equivalent to the magnitude of our force vector F times sine of theta, where theta is the angle between our r and F vectors. And so this formula is going to give us the magnitude of our torque vector, or the magnitude of our cross product operation here in general. And it looks very similar to our formula for the dot product. The only difference is, well, now we have a sine of theta instead of cosine of theta. Another big difference between the dot product and the cross product is the dot product produces a scalar, right? It's just the magnitude of those two vectors times cosine of the angle between them, while the cross product is more than that. The magnitude of the cross product is kind of similar. It's the magnitude of your two vectors multiplied together times sine of the angle between the two vectors. But the big difference between the cross product and the dot product is the cross product is also going to give us a vector. In the case of torque, we call that vector tau. And so we know how to find the length or magnitude of this vector that is going to come out of the cross product, but we still have to talk about the direction of this vector. And so the direction of the vector that we get out of a cross product is really going to be following the situation that we are looking at here, where we are tightening or unscrewing a bolt. And that's going to follow basically that old saying of righty-tighty, lefty-loosey, or in general what we call the right-hand rule. And so if we look at the situation in the picture we have drawn here, if this is our wrench vector R, or our position vector R, and our force vector is pushing in this direction, then that would create some counterclockwise rotation, or you're turning it left essentially. And well, we know lefty-loosey, well, if we are unscrewing a bolt and rotating that wrench counterclockwise around the bolt, or that axis of rotation, then that's going to cause the bolt to unscrew upwards. If we were to reverse the direction of our force vector and cause the rotation to be clockwise, well, in that case, we would be tightening the bolt, and the direction of that turning effect would cause the bolt to be moving downwards. And so we can also define torque using this cross product notation. The torque vector is equal to that position vector R crossed with our force vector F, and the direction of our torque vector, or the direction of the vector that comes out of a general cross product, is given by that right-hand rule. You're going to take your fingers and point them in the direction of that first vector R, and then rotate them towards the direction of your second vector F. And the direction that your thumb is pointing is always going to give you the direction of the vector that comes out of your cross product, or in this case, the torque. So we use flipped images when recording these videos, so hopefully I'm not messing this up. But the idea is, if we are taking a wrench and rotating it clockwise, then that'll cause the wrench to be screwing down and tightening a bolt. And if we take a wrench or a screwdriver and rotate it counterclockwise, that'll cause us to be untightening or unscrewing the bolt or screw. So just one more little visualization for now for the right-hand rule. And so if we have two vectors R and F, they're always going to form a plane, or we can always span a plane using those two vectors. And if we think about taking our right hand, pointing our fingers in the direction of our vector R, and then curling them towards the second vector in our cross product, in this case our force vector F, then that curling effect is going to cause our thumb to point in a certain direction, and the direction our thumb is pointing is going to be the direction of the output of our cross product, or in this case our torque vector. And so if the plane that our R and F vectors lie in is like the XY plane, or a perfectly horizontal plane, then our torque vector, or our cross product vector, would be pointing vertically up if we are rotating counterclockwise, or vertically down if we are rotating clockwise. If the plane that is spanned between our two vectors R and F is askew or tilted, then our torque vector, or the vector that comes out of our cross product, will also be tilted and will always be perpendicular to that plane between our two vectors. That's another important property of this cross product that we'll write down later. The vector that we get out of our cross product is always going to be orthogonal or perpendicular to the two vectors that were in the cross product. So just one more time, the direction of tau, or the vector that we get out of our cross product, or the torque in this case, is given by the right-hand rule, or in other words, the direction a right-threaded bolt would move if we are unscrewing or tightening that bolt using a wrench and applying a force to that wrench. So being able to calculate and find these vectors related to torque is very important and very useful in applications like physics, but this expression shows up in more than just torque-like applications. It shows up all over the place in mathematics, and for that reason, we give it a special name and we generalize this process and call it the cross product. All right, so now we finally had the definition of our cross product written down, so let's go ahead and go over it. And so if A and B are two non-zero three-dimensional vectors, the cross product between A and B is going to be denoted as A cross B, and it's going to be equal to the magnitude of A times the magnitude of B times sine of theta, where theta is the angle between our two vectors A and B, and that's going to be given a direction of n, where n is the unit vector that is orthogonal or perpendicular to both vectors A and B, and is given by the right-hand rule between our vectors A and B. And so here, this formula we are first looking at for our cross product is really like our geometric version of the cross product formula, similar to how we had that geometric version of our dot product formula. We also, for our dot product formula, saw how to compute it using the components of the vectors involved in our dot product, and that's what we're going to work towards next. How do we also evaluate a cross product, not using this geometric definition like the magnitude of our two vectors, the angle between them, and this weird perpendicular unit vector? How do we compute the cross product just using the components of our vectors A and B? Well, to figure that out, we need to start with the basics of how do we take the cross product between our basis vectors, and then we'll also need to use some important algebraic properties of the cross product. A lot of you know that Mike and I use a Lightboard to record these videos, and part of the process of using a Lightboard to make these videos requires us to flip the image around, and that's why it always looks like we're writing with our left hand even though we are both right-handed. Normally this doesn't have an effect other than making us look like we're ambidextrous. However, when we're starting to do this three-dimensional graphing and talk about things like the right-hand rule, it is beginning to have an effect. And so you might notice in some of the videos, things like the right-hand setup for our axes will be messed up and flipped around, and how we describe the right-hand rule might look a little funky. So everything should look normal and correct in this video. However, it's going to cut into our other video where we were recording previously without taking this into account. So after we cover this, things might get flipped around yet again. And so what I want to talk about in this video is how to find the cross product between the different combinations of our standard basis vectors, those I, J, and K vectors. Remember, I is the vector that points in the positive X direction, that's a unit vector. J is the unit vector in the positive Y direction, and K is the unit vector in the positive Z direction. So if we think about the geometric definition of the cross product as the product of the magnitude between the two vectors and sine of the angle between them, our three unit vectors are all mutually perpendicular to each other. So no matter which combination we look at, we're going to have that angle between them be 90 degrees, and that's going to make that sine factor equal to 1. The magnitude of these unit vectors are also 1, so the magnitude of the vector we get out of these cross products is also going to be 1. So any combination we look at here is going to produce another unit vector. We are now just going to try to figure out the directions of those unit vectors, and that's going to be done using the right-hand rule. And so let's go ahead and look at our first combination over there of I cross J. Well, if we take our fingers and point them in the direction of our unit vector I, and then cross them towards our other vector in our cross product J, the direction our thumb is pointing is going to be the direction of the vector that comes out of our cross product. And as we can see here, that's going to give us the unit vector in the positive Z direction, or our K unit vector. Well, now we're going to look at the cross product in the opposite order. So what is J cross I going to look like? Well, if we want to now look at the cross product between J and I, well, we have to start by pointing our fingers in the direction of our unit vector J, and then cross them towards our other vector I. And well, J cross I is going to give us a unit vector that points straight down, which is going to be in the direction of negative K. All right, up next, let's go ahead and look at J cross K. All right, so now if we're looking at J cross K, we're going to point our fingers in the direction of our J vector and then curl them towards the direction of our K vector, and our thumb is going to point in the resulting vector's direction from our cross product, and that'll be our I vector. And so if we flip that previous cross product around, we'll be looking at K crossed with J. And well, if we do that right-hand rule for K cross J, the direction of our thumb is going to point in the direction of negative I. So K cross J is going to be equal to negative I. All right, only a few combinations left to go. Up next, we're going to look at k crossed with I. And so again, using our right hand rule, we're going to point our fingers in the direction of the positive z-axis or in the direction of k, and then curl them towards our vector that points in the I direction or in that positive x direction. And our thumb is going to be pointing in the direction of the vector that comes out of this cross product, and we see that that is going to be in the direction of the positive y-axis, and that is going to give us our j vector. And to finish it off, we can now see as well that I cross k is going to be equal to negative j. And so just very quickly visualizing that, I crossed with k is going to have our thumb point in the direction of negative j. And so now that we know how to find the cross product between all the different possible combinations between our basis unit vectors, I, j, and k, we can put this together with some of our other properties of the cross product and figure out how to take the cross product between any pair of three-dimensional vectors. So one vector cross product combination for our standard basis vectors that we did not include in our original list of 6 is I cross I, or j cross j, or k cross k. And it's actually important to know what happens in this situation as well. Whenever we take the cross product between a vector and itself, we don't get 0, but we get the 0 vector. And this actually makes sense if we think about our geometric interpretation of the cross product, because if the two vectors are parallel, then the angle between them is going to be a 0-degree angle, and sine of 0 degrees is 0, so that would zero out our entire cross product, multiplying whatever that n vector could possibly be by 0, making it a 0 vector. It also makes sense if you think about our motivation of torque. If your force vector doesn't have any perpendicular component to your wrench, but is entirely parallel to your wrench, it's not going to rotate your wrench at all or create any torque, so your torque vector should also be 0 in that case. So whenever we take the cross product between a vector and itself, we're going to get the 0 vector. And that's true for I cross I, j cross j, k cross k, or any vector crossed with itself. That always zeroes out and gives us the 0 vector. We started off by defining our cross product using this geometric interpretation or formula that was motivated by torque or tightening or unscrewing a bolt. We then figured out, using the right hand rule and that first definition, how to evaluate the cross product between any pair of our basis vectors I, j, and k. And what we're working towards next is figuring out how to evaluate the cross product just using the components of our two vectors a and b. And well, to figure that out, we're going to need to use a few of our algebraic properties of a general cross product, and that's what I have listed here in these 4 properties of the cross product. The first one we saw in our examples of finding the cross product between our unit basis vectors, but it's true in general for any vectors involved in the cross product, and that's that a cross b is not the same as b cross a, but it is the same as negative b cross a. So we don't get the same vector out of our cross product if we flip the direction of our cross product. If we flip the direction of our cross product, we have to also flip the direction of that original vector from the original cross product. And our second property helps us work with scalar multiplication of a vector within a cross product. So if c is a scalar and a and b are our two three-dimensional vectors, then a scalar multiple of a crossed with b is going to be the same as taking a cross b and multiplying that vector by the scalar c. Or we could multiply our second vector b by that scalar c instead, and then take a cross the scalar multiple of b with c. So the scalar multiple, we can just kind of pull in and move around our cross product as we want. And our next two properties combined are just giving us the distributive property for our cross product. If we were taking a crossed with the sum of two vectors b plus c, well, we can do a cross b plus a cross c. Or similarly, if the sum of our two vectors creates that first vector in our cross product, we can expand this or distribute our cross product throughout this sum. We're going to get a cross c plus b cross c. All right, so now we're going to put all this together to finally figure out how to evaluate the cross product using the component form of two vectors. So let's go ahead and let our first vector in our cross product a be defined by a1i plus a2j plus a3k, and our second vector in our cross product have components of b1, b2, and b3, or b1i plus b2j plus b3k. Then if we want to evaluate A cross B, we can do so by writing the cross product in terms of the components of the two vectors and then using these algebraic properties of the cross product along with what we know about taking the cross product between these basis unit vectors I, j, and k. So we're going to have a1i plus a2j plus a3k. That's our first vector, and we're going to have to cross that with our second vector, which has components of b1i plus b2j plus b3k. Okay, so how do we get started in evaluating and simplifying this cross product formula and figuring out a shortcut for doing all this with just the components of A1, A2, A3, and B1, B2, and B3? Well, the first property we're going to have to use is our distributive property for our cross product. So we're going to have to distribute A1i throughout the three components in our second vector B. Then we'll have to distribute A2j throughout that vector B again, and then do it a third time around for that third component of our first vector, A3k. So the first part is going to look like A1i crossed with the first piece of our second vector. That'll be B1i. Then we have to add to that A1i crossed with B2j. A1i crossed with B2j. Then we have to do this one more time, distribute A1i to B3k. And that third vector is going to be looking like A1i crossed with B3k. All right, I'm going to do this over 3 lines. The first line is from distributing A1i throughout our second vector using the distributive property for cross products. The second line will be for distributing A2j, and the third line will be for distributing A3k. So a lot of distribution and expansion is going on here, but in the next couple steps, we'll be able to eliminate some of these terms and combine and simplify the rest of them. And the first thing I want to point out is, remember, any cross product involving the vector with itself or a parallel vector is going to give us 0. So it looks like we have some of this going on here, right? For that very first cross product, we have A1i crossed with B1i. And if we wanted to, we could pull out those constant factors of A1 and B1 and write this as A1 times B1 times I cross I. But what do we know about I cross I? That's going to give us a 0 vector. Similarly, this piece down here, A2j crossed with B2j, will involve a cross product with j cross j, and a j cross j cross product will also give us a 0 vector. This happens one more time when we are crossing A3k with B3k. That will also give us a 0 vector for that piece of our cross product. So that's some good progress. We've gone from 9 terms in the original expansion of our cross product using components down to 6 terms, but we can take it a few steps further and eventually whittle it down to just 3 terms. So let's go ahead and keep working towards that. So for our next piece, we have A1i crossed with B2j. Well, we can use that property that lets us bring those scalar factors of A1 and B2 out. And then we're just looking at what is left is going to be I cross j. But what do we know about I cross j? I cross j gives us k. So the very first cross product in our expanded version went to 0. The next cross product, A1i crossed with B2j, we can simplify and rewrite as A1 B2 times k. So now let's go ahead and look at our next piece. A1i crossed with B3k. Well, we can bring these constant factors of A1 and B3 out. And then we're going to be left with I cross k. And well, what do we know about I cross k? It's equal to negative j. So I'll bring the negative sign out front and put the j at the end. So let's keep doing this. So our next piece we have to try to simplify is A2j crossed with B1i. So again, we'll bring those constant factors, those coefficients of A2 and B1 out front. And then what's left over is what are we going to get from j crossed with I? And well, if we go to our little scratch work over here, looks like j crossed with I is going to give us negative k. So again, I'll bring the negative sign out front and throw that unit vector of k at the very end. Let's see what's left over in our second line is a2j crossed with b3k. So we know what we're going to do with the constant coefficients. The a2 and the b3 will come out front. And then next we have to figure out what happens with j cross k. Well, according to our list of scratch work from before, j cross k is going to give us positive I. So that's very good. We've taken care of that smaller cross product. Now we have two left. Up next is going to be a3k crossed with b1i. So we have a3 and b1. And then what happens with k cross I? Let's try to find it over here. Looks like k cross I is going to give us positive j. So that takes care of that one. And this is our last non-zero smaller cross product to take care of. The coefficient is going to be a3b2. And then what happens with k cross j? Well, k cross j is going to give us negative I. This is great, and we're almost there. We almost have our final version of how to evaluate a cross product using just the components of the two starting vectors, a1 through a3 and b1 through b3. Now all we really have to do is combine like terms and wrap this all up. So the first term in our vector is going to be the terms involving I, or I should say the first component of our overall vector is going to be the components involving I. And so it looks like we have two I components, and the coefficients are a2b3 minus a3b1. So we can write this as a2b3 minus a3b2. And those are the coefficients in front of our I unit vector. So that takes care of those two pieces. Up next, let's look at our j components. Our first positive one is going to be a3b1j, and then we have to subtract away from that a1b3 times j. So our overall final j component is going to have a coefficient of a3b1 minus a1b3. And now to totally finish it off, we just need our k components. The first term in our k components coefficient is going to be a1b2, and our second term is going to be negative a2b1. So now we have the cross product formula using the components of our two starting vectors. It's a little bit of a complicated formula, a bit hard to memorize, but up soon or up next, we'll talk about a shortcut for remembering this cross product formula. All right, everyone, so we just figured out our cross product formula for using the components of our two vectors A and B, but it is a pretty complicated formula that is a little bit hard to memorize. So before we look at an example using our component formula for our cross product, I want to talk about another way to help us memorize this formula using the concept of a determinant. So determinants are a neat little mathematical object used to help us organize some information. They're a lot more important and seen a lot more and discussed more in depth in a class like linear algebra. For us, we're just going to use them as a system to help us memorize this component formula for our cross product. We're going to eventually use an order 3 determinant to help us represent a cross product using a determinant, but first we're going to start with determinants of order 2. And so this is what a general order 2 determinant is going to look like. It's a lot like a matrix or an array, where you think of the first row as maybe representing your first vector and your second row as representing your second vector or the entries from your second vector. And then instead of the kind of square brackets that we use for matrices, we're going to use just vertical bars like our absolute value or magnitude bars. And what an order 2 determinant is denoting is an operation that we compute with these 4 entries. And so the order 2 determinant is always going to evaluate when it's written as such as a1b2 minus a2b1. An important observation to make that helps us remember how to evaluate this order 2 determinant is that the product of this left diagonal gives us our first term, a1 times b2, and the product of this left diagonal is going to give us a2 times b1. So it's like we take the right diagonal and then subtract away from it that left diagonal, and that'll give us a1 b2 minus a2 b1. All right, so now that we've covered our order 2 determinants, we're ready to talk about our order 3 determinants, and we can actually go up to order 4 or higher determinants, but that's not necessary because for the cross product, we really only need these order 3 determinants. And the way we kind of at least initially start evaluating these order 3 determinants is by breaking them down into order 2 determinants. So let's go ahead and show you how to do exactly that. So the way to evaluate an order 3 determinant in general is using this concept of cofactor expansion, which is covered in a class like linear algebra. I'm just going to give us kind of the end result of that cofactor expansion. We're first going to break this down into 3 order 2 determinants, and the first one is going to look like the constant A1 multiplied by the order 2 determinant of B2, B3, C2, and C3. But that is not it. What we then have to do is subtract away from this A2 multiplied by the order 2 determinant that is going to look like B1 and B3 in the first row and C1 and C3 in the second row. And then the third piece that we add on to this is going to be a positive A3 coefficient multiplied by another order 2 determinant that is going to look like B1, B2 for that first row, and let's see, C1 and C2 for the second row. And so this may also look like an even more complicated formula to memorize or use than our formula for the components that we cooked up with the first time around, but there's a really nice pattern here that we can observe that makes this easier to memorize. And so notice these coefficients that we bring out in front of the order 2 determinants are just the entries across the first row of our order 3 determinant, and they're alternating in sign. So it starts with positive A1, then negative A2, and positive A3. What I want us to notice next is this first order 2 determinant, the B2, B3, C2, C3 determinant. It can be viewed in our original order 3 determinant by covering up the column and row of A1. So A1 is that coefficient in front of our order 2 determinant. The order 2 determinant that we have to multiply A1 by is what is left over from our order 3 determinant when we cover that column and row involving our coefficient A1, right? So what we have left over is B2, B3, and C2, C3, and the same pattern is going to be true for our next 2 pieces. So now if we go to our next piece with the negative A2 coefficient, if we cover up that column and row involving A2, what's left is going to be B1, B3 in that first row, and C1 and C3 in that second row. And moving on to the final piece, cover up that column and row involving A3, and the 4 entries that are left to make up our last order 2 determinant of B1, B2, and C1, C2. Up next, I want to show you how to express a cross product using an order 3 determinant. All right, so the way that we can represent our cross product formula using an order 3 determinant that will, in the end, after we evaluate that determinant, give us the same exact formula is going to look like this. So we're setting up an order 3 determinant. That first row of our determinant is actually just going to be our 3 basis vectors I, J, and K. The second row in our order 3 determinant is going to be the entries for our first vector, A. So those entries should look like, in general, A1, A2, and A3. And our final row will just be the entries from our second vector in our cross product. That'll be B1, B2, and B3. All right, so now let's go ahead and actually evaluate this order 3 determinant all the way out to see that we get the exact same formula that we cooked up earlier for the cross product using the components of our 2 vectors. So as we see down here, the first thing we do is we break our order 3 determinant up into the sum and difference of 3 order 2 determinants. So the coefficients in front of these order 2 determinants are going to be the entries from our first row of our order 3 determinant with alternating signs. So instead of A1, we have I. That's going to be multiplied by the determinant that is made up of A2, A3, B2, and B3. Remember, we can figure out the entries of that order 2 determinant by covering up the row and column of our coefficient I. So then we have to subtract away from this A2, which is not this A2, but the A2 in the general order 3 setup, or the second entry in our first row. So we're subtracting away j multiplied by another order 2 determinant. What is that one going to look like? Well, we can figure it out by covering up that row and column involving our coefficient piece j, and what's left over is a1, a3, b1, and b3. So a1, a3, b1, and b3. That finishes off our second order 2 determinant in this breakdown. And to get our third and final piece, we have to do k, or a3 in this general setup, multiplied by one more order 2 determinant. And that one's going to look like a1, a2, and b1, b2. All right, so let's go ahead and finish this breakdown of our cross product using order 3 determinant by evaluating these order 2 determinants. So we're going to have our basis vector I multiplied by the outcome or output of this order 2 determinant. And remember, to evaluate the order 2 determinants, we can do that nice little right and left diagonal multiplication and subtraction. So we're going to have a2 times b3, and we subtract away from that the left diagonal of a3 times b2, and all of that gets multiplied by our unit basis vector I. And so what is the first component of the output of our cross product formula? It's a2b3 minus a3b2 for that first or ith component. All right, so up next we have to combine this with negative j times the output of this order 2 determinant. And so, well, what does the right diagonal give us? That's going to be a1 times b3. And then we have to subtract away from that our left diagonal, which is a3 times b1. And then our final piece to finish all this off is going to be adding to all this k times the output of this third order 2 determinant. Its right diagonal is going to give us a1 times b2. And its left diagonal is going to give us a2 times b1. And we have to subtract that one away, minus that a2 times b1. And so let's see. Our first component we already saw matched up perfectly. The second component looks a little different, right? This one looks like a1b3 minus a3b1, but remember, that's all multiplied by negative 1 or negative j, and that's going to cause these signs to flip, and it'll turn into positive a3b1 and negative a1b3. So it actually matches up as well. And the third one is pretty clear to see that for our last or kth component, the coefficient really is just a1b2 minus a2b1. So we really do get the exact same formula, whether we just kind of brute force memorize that component version or use an order 3 determinant to help us memorize the cross product formula. This whole process of this cofactor expansion can also be a bit tricky to memorize, so there's actually yet another shortcut that works just for evaluating these order 3 determinants. And I want to show you that next. And so this next shortcut for evaluating just these order 3 determinants is very quick and very nice, and it's still kind of using the right and left diagonals, but slightly differently. And so what we have to do for the ith component is start at the first entry involving I, which is that first entry of row 1, and then ignoring that I, look at the rest of that right diagonal for that first row. So the rest of that right diagonal is going to give us a2 times b3, and that is the first term of the coefficient for our ith component. So it's like we're going down this right diagonal to figure out what are part of the coefficients in front of I. Well, it's going to be a2 times b3, but what are the rest of the components involved in computing? But what are the rest of the coefficients involved in computing our ith component? It's going to be negative a3 times b2. And so that's going to be these two pieces, a3 times b2. And so now a way to visualize this is still thinking about starting at I right here, or our first entry in row 1, but now we travel to the left and down that diagonal instead of to the right and down. So if we try to go down and to the left, there's nothing over here. So what we do is we wrap back around to this side. You can kind of think of it like an old school video game, or if this text was actually wrapped around a circular cylinder. Then as we go down and to the left, we'll intercept A3 and B2. And so we take that right diagonal from I and subtract away from it that left diagonal from I. So we subtract away A3 times B2. And I just realized that first one should have been A2 times B3, not A3. So let me fix that right now. But this difference between the right diagonal and the left diagonal starting at I gives us our coefficients for the ith component. And we can actually repeat this without needing to do that weird alternating of signs like we did for cofactor expansion. So next we go to our jth component, or our second entry in our first row. So what is the right diagonal starting at j going to look like? Well, we go down and to the right and hit A3, and then we go down and to the right again. But now we can't go down and to the right over here. There's nothing there. So we wrap back around and hit B1. So going down the right diagonal gives us j times A3 times B1. So we'll write A3 and B1 there for now. And if we go down the left diagonal starting from j, we're going to subtract this away from our previous coefficients. And that's going to give us a minus A1 multiplied by, as we continue down and to the left, we have to wrap back around and hit B3. So it'll be a minus A1 times B3. And that gives us our jth component. And notice that matches up A3B1 minus A1B3. And we can do this one more time for our kth component. And so now we are starting at k and going down the right diagonal. We have to wrap around right from the get-go. But that right diagonal will eventually give us A1 times B2. And we subtract away from the right diagonal the left diagonal that starts at k. And that left diagonal will involve A2 times B1. And so using these nice right and left diagonals and differences formula, we can evaluate a 3D determinant or our cross product formula much quicker. And it's pretty easy to memorize as long as you get this right and left diagonal stuff down.